Hello everyone, welcome to our channel Mathematics Parshala. This is a problem of CSIR NET December 2023 Mathematical Sciences. This is a question from Linear Algebra Part B. The question ID is 704030. See the question first. Let A be an n by n matrix with complex entries. If n greater than equal to 4, which one of the following statements is true? So let us first read one by one the options. First option says that A does not have any non-zero invariant subspace in Cn. Option 2 says that A has an invariant subspace in Cn of dimension n minus 3. Option 3 says that all eigenvalues of A are real numbers. Option 4 says that A square does not have any invariant subspace in Cn of dimension n minus 1. Let us first uh, recall the invariant subspace. A subspace W is said to be invariant subspace under A if AW subset of W. So see first for option 1 and option 4, if we take simply A equal to identity matrix or identity operator, the same thing, then clearly all subspaces will be invariant, because for this operator IW is equal to I actually, so IW subset of W will be satisfied. So for this operator, option 1 that says that it does not have any non-zero invariant subspace in Cn, that is not true. So option 1 is not true in general, because if we take A equal to I, the option 1 will not be true. So this is not the correct option. And similarly, for option 4, then A square will be also I square, that is I, and it says that A square does not have any invariant subspace in Cn of dimension n minus 1, but in that case all subspaces will be invariant subspace. So if we take a subspace of dimension n minus 1, that will be invariant, but but here option 4 says that A square does not have any invariant subspace in Cn of dimension n minus 1. So option 4 is not true in general. Now look at option 3. All eigenvalues of A are real numbers. So if we take a matrix such that which is skew symmetric, that is AT equal to minus A, and at least one eigenvalue is non-zero, we know that for a skew symmetric matrix all eigenvalues of A are will be either 0 or purely imaginary. So at least one eigenvalue which is not 0, that will be purely imaginary. So for this A, option 3 is not correct, that is all eigenvalues of A are real numbers. So this is not true in general. So option 2 must be the correct option, and for this we are not going to prove this in details, but see, uh, here we have to assume that n greater than equal to 4. So in particular, if we take n equal to 4, that means A is a uh, matrix of order 4 by 4, matrix order 4. So then we have to find an invariant subspace of dimension n minus 3, that is 4 minus 3, that is 1. So take one eigenvalue of A. Since A is a complex matrix, there are all eigenvalues are there, because the characteristic polynomial will be written as the product of linear factors, because it is in C and C is algebraically closed. So all polynomials will be split there. So take one eigenvalue lambda from C and take one eigenvector corresponding to this lambda, say x. That is, we have Ax equal to lambda x. Now see clearly, if we take this subspace, say W generated by this element x, so this is subspace of dimension 1, that is here 4 minus 3 n minus 3, and also clearly this is a invariant subspace, because if we take any element, say belongs to W, so that element will be of the form Cx, scalar multiple of x, and we have to prove that A of this element will also belong to W. Now A of Cx will be equal to C Ax, and since Ax equal to lambda x, so this is C lambda x. It is also scalar multiple of x, so it belongs to W. So we have AW subset of W. So W is an invariant subspace in Cn of dimension n minus 3. Exactly in similar manner, if we take n equal to 5 for the next case, n equal to 5, then if we take one eigenvalue lambda and corresponding to if there are two eigenvectors, linearly independent eigenvectors corresponding to this lambda, say x or y, then clearly if we take the subspace W generated by these two elements, since x and y are linearly independent, then the W will be a subspace of dimension 2, that is here n minus 3, 5 minus 3, and also clearly for in the uh, as in the previous case, it can be proved that W is invariant, that is AW subset of W. And if uh, this is the case that there exists exactly one eigenvector corresponding to this lambda, then we take another eigenvalue, say mu, and take one eigenvector corresponding to this mu, say z, then we take the subspace generated by this x and this z, and this will be a subspace of dimension 2 which is invariant. And also it may be happen the worst case, that means suppose that A is a matrix of order 5 of complex entries, and it can happen that A has only one eigenvalue, say lambda, and also there is one eigenvector, exactly one linearly independent eigenvector corresponding to this lambda. So then we have the eigenspace E lambda, the dimension of this eigenspace will be 1, that is our geometric multiplicity of A corresponding to this lambda will be equal to 1, and then in this case A will be of this form, say, so that means there is since geometric multiplicity is 1, that is there is only one Jordan block corresponding to this eigenvalue, and since A is a matrix of order 5, so that means this block will be of order size 5. So there is exactly one block of size 5, that means the Jordan canonical form of A will be lambda 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 in this diagonal, and super diagonal is 1 and other elements are 0. So in this case we can consider the matrix A minus lambda I, and we can call it B, and then our B will be of the form in this case, that is 0 0 0 0 0, here it is 1 and other elements are also 0. So in particular lambda may be 0, then B will be equal to A. Then we can have B, we have a particular form that B x1 x2 x3 x4 x5 will be, in this case it will be, just you verify you by yourself, that is it will be x2 x3 x4 x5 and here 0. So in this case we have to consider a vector and corresponding to the t cyclic subspace of that vector. So in this case if we take a simply vector v equal to say 0 1 0 0 0, then clearly here AV will be equal to 1 0 0 0, just verify, and a square v will be equal to 0, that is 0 0 0 0 0. Then consider the t cyclic subspace of v generated by v, that is VAV, this subspace. Actually v, a v, a square v and so on, but all the elements are 0 after from this a square v. So this is a t cyclic subspace of dimension 2, and every t cyclic subspaces will be invariant subspace, and this is a subspace of dimension 2, that is 5 minus 3, n minus 3. So in this way we can prove this result. So option 2 will be the correct option. So here option 2 is the correct option, and 1 3 4 are not the correct option. This is the solution of this problem.